Good morning. The keynote ran a little late, so I'm going to try to go fast. I will try to leave time for questions, no guarantees. As he said, I am Philip. I'm a software engineer. I've been working in Python for about 10 years, and I mostly build web apps, and I'm starting to build chat bots and Twitter bots and Slack bots because that's really fun. What we're going to talk about today, we're going to talk about not what happens in the Python bootstrap process when you type Python and press enter. If you were hoping for a talk on Python internals, sorry, you can leave. I'm not going to feel bad about that. Like, there's lots of discussions about Python internals on PyVideo. You can go check those out. What we're going to be talking about instead is what it looks like from the operating system's point of view when you start up a Python process and give it text. I will also add a caveat to say I am not really an expert on this subject. This whole presentation came about because myself and a friend had this question: what happens when you type Python and press enter? And we spent a bunch of time figuring out a way to convey the answers to these questions, and then we made a talk about it, and now I'm here. So let's walk through what we're actually going to be discussing. So if you are at your shell and you type Python and you press enter, you get the Python shell. And then let's say you want to use the Python shell to do a really simple calculation like 2 plus 2, you get 4. Hopefully that's obvious. You're like, okay, great, I've done this calculation, I want to exit, I do Control-C. Oh, wait, that doesn't actually work in Python, right? I have to do Control-D to get back out of the shell, or get back out of the interpreter into the shell. We're going to talk about how that all looks from the operating system level. Everybody good so far? Great. So we're starting with a shell. This is kind of the beginning and the end of what we're talking about. The shell is your interface to the internals of the computer. This is the bash shell. That's the framework that we're going to be working in. Bash shell is pretty common. If you use a different shell, a lot of it's going to be really similar because it's not necessarily shell specific. But you can also kind of follow along with this presentation. We'll be talking about commands, and they are the actual output of the commands, but no live demos because those never actually work. So you type Python, and the first thing the shell needs to find out is, where does this thing that you have just asked me for live? So the shell is looking for a program, and the way it looks for a program is in a path variable. The shell is a program. Programs can have variables. All variables in bash in the shell are strings, and one of those strings is path. You can see it, your path on your computer by doing echo path, just like that command right there. And if you do that, you'll get the list of all of the paths that your shell knows about. Because all shell variables are strings, the way to separate a string into substrings is to use colons, like you see here. And so the shell is going to go through each of the paths that it finds, looking for the program that you asked for, which is Python. So if I were to type Python, it would start in /home/paulproteus/bin. There's no Python there. Okay, try the next one. Look in user bin. Hooray, we're on a Linux system. We're on Ubuntu, to be specific. Python does exist in /user/bin. Yay, we have found Python. But what does that mean that we have found Python? The shell is looking for something that it can execute because you've given it a command. What does executable mean in the context of this system? So one way we could do that is we know where Python lives because we found it in user bin, and we can run a program called hexdump to actually look at the bytes that make up the Python program. And if we do that, we see these first kind of leading characters, 7F, 45, 4C, 46, that translate into ELF. Okay, that seems maybe useful because it's at the beginning of the file. We know that things at the beginning of the file are normally directives to other programs. Let's run a program that's a little bit more useful, and we'll run file on user bin Python, which is another program for inspecting programs. File on user bin Python returns ELF 64-bit LSB executable. Some Googling tells us that ELF stands for executable and linkable format, and this is how the shell knows that when it's searching through those list of paths, it's found something that can be executed. There are lots of types of things on an operating system that fall into the can be executed category, but this compiled Python binary matches the executable and linkable format, and so bash goes, aha, I have found it. I don't write C, I write Python. If I were writing a shell in Python, this is the algorithm I would write, or at least something like that, to replicate this kind of like search for a program and execute methodology. It's going to go over everything it can find in the path. It's going to see if Python actually exists in that point, and then it's going to try to return it. Otherwise, it's going to raise command not found. Again, this isn't the actual algorithm because it's Python and not C, but if you were writing a shell in C, which I haven't seen anybody do yet, but that would be awesome, you might use something like this. Yeah, I can't imagine that it's really fun, actually. Okay, so we have our program, Python. Programs run in processes. This is an abstraction of the bash process. It's a little container. It's called bash. It's got a PID or a process ID of 1221. And so you think, okay, I have Python. I have this process for Python to run in. I might do something like exec Python to start up the Python program and run it. Okay, great. But there's a problem. If Python dies for whatever reason, if it's killed internally or externally, I don't have any process left. If you're on a Mac, you don't see this as much on Linux, but if you're on a Mac, you might have seen something like after a command runs, because you've like double-clicked an icon or something, you might see process completed. That's what we're trying to avoid here. That means there's nothing you can do with this shell anymore. It's exited, you're done. So what we really want is for bash to be able to make a copy so that it can run Python in the copy, and then if Python dies for any reason, you have the shell to go back to so you can continue running commands or doing whatever you were going to do. And this is what processes on Unix systems do. They use a system call called fork. A system call is an API for a program to ask the kernel to do something, the kernel being what runs your entire operating system. And this particular system call says, hello, kernel, please make a copy of myself and increment the process ID number. Make a new process that looks like me, but with a different process ID number. And the kernel goes, yes, of course. Here's PID 1222, and it's also called bash. And bash goes, great, fantastic. I'm going to take this copy of myself, and I'm going to call exec with the program that we found earlier, and I'm going to exec Python. So now we have the original bash process, and we have a separate process called Python. So if anything happens to Python, we can dump back to the bash process, and things work the way we expect them to work. This is how processes are actually spawned and exec'd on Unix systems. You can actually look at the man pages for these system calls and see a whole bunch of really interesting options that you could use in your programs if you wanted to do interesting things that could crash your operating system. Okay, so you can actually explore this. There's a great Unix utility called pstree that if you run it on your system, it will show you a tree of all of the forks and execs that your system has gone through to get you where you are. So in this example, we're working on a box that we've SSH'd into rather than working on a local box. So you see there's that init process at the top. That kind of kicks off the whole system. There's a cron process running in the background. There's an SSHD for the SSH daemon. There's a couple of bash shells. And then there's a fork and exec for Python and a fork and exec for pstree. All right, quick recap. Process creation. Find the binary in the path variable, fork the current process to make a new process to run the program in, and then exec that program in the new process. Cool. You might be thinking, I know I was, wait a minute. If the shell looks for an executable based on what I type at the prompt, how does it handle options I pass in like -v? If you've never run Python-v, it's kind of interesting. It'll show you everything that's being imported, basically the Python things that are happening behind the scenes when you start up the Python interpreter. It won't show you the full bootstrap process, and again, we're not covering that in this talk, sorry. I do recommend you go try to like dig into the Python source code because you'll find some really weird places where Python inits things twice for apparently no reason that we could determine when we were looking at this, but that's neither here nor there. So, what does the shell actually do when it encounters options on a command? It parses that list of things that you've given it, because everything is a string really at the terminal, into a list of arguments called creatively the arguments list. And that arguments list is another option to the exec command that actually gets passed to the running program. So it looks for Python, it finds user bin Python because that's the executable, and then it puts everything into the arguments list. And you'll notice that the first argument in the arguments list is Python. So argv0 is always the thing that you are asking for. However, we did not pass with -v. So for the purposes of the rest of this talk, our argv is just Python, right? So this is our current working model of the Python process. It's a process, it's got a process ID number, it's called Python, and it's got an argv list of Python. Okay, so we've got an open Python shell, but we still want to do our simple calculation. The next thing we need to cover is how does the operating system handle input and output into Python and back out? And in order to explain that, I need to show you this picture of a really old machine from the long ago days of the 70s and 80s. This is a teletype machine. You would sit at one of these machines if you wanted to use a computer, and you would type your messages, and they would go over a telephone line into a server somewhere. And then the response to what you typed from the server would be sent back over the telephone line. Teletype. Note that there's actually paper in this machine. Everything you typed and all the responses will be printed on this paper. It's kind of wild to think that the print commands in modern languages harken back to the days when you were actually printing on paper, and we have never updated our paradigms, right? This is like, we're getting close to 40 years of still thinking, the operating system still thinking that it's printing on paper. Yeah, exactly.
For that matter, why do we have 80 columns as standard monitor resolution?
Because this was 80 columns wide.
And it was 80 columns wide because you had 80 characters in a punch card.
Right. As a follow-up, I could walk you through, after this talk, I could walk you through a really interesting discussion about how the space shuttle, the size of the space shuttle was determined by the standard width of a Roman road. I can walk you through that whole thing. Anyways, so the other interesting thing is that this machine was a terminal to the server, the interface at the terminus of the telephone line. Language starts making sense when you start learning more of the history. So we don't have physical terminals like this anymore. We have pseudo-terminals. And the pseudo-terminal that we're going to be talking about today, as an example, is /dev/pts/3. Again, we're on an Ubuntu system. This is how things are organized. And these pseudo-terminals are physical terminals that are replicated in software so that you can have multiple terminals to your machine and they work to the kernel the same way that things have always worked. So Python needs a way of grabbing onto these pseudo-terminals so it can take input and it can send output, and it's going to need a couple more if you have errors. And the way it grabs a handle onto these pseudo-terminals is with file descriptors. So there's the Python process, and you can think of it as having links to different pseudo-terminals. So link 0, file descriptor 0 on dev pts3, it's got a more common name that you might know of as standard in. If you see standard in, that's file descriptor 0 on the current process that you're working in. So when we do something like type 2, that 2 character goes into the kernel through this termios layer that works to mimic that old paper terminal telephone line system, and eventually it gets sent to the file descriptor on the Python process, and the Python process receives the 2 press. You can see this kind of happening in real time using a command called strace. Has anyone here ever straced Python? Yeah, okay, a couple, great. It's a trip. You're going to see a lot of output that you weren't expecting because it's basically all of these system calls that Python is making when it tries to start itself up. So we're going to skip a bunch of that because for the purpose of this talk, we care about kind of the last one after you start the shell, and it's this read system call. You see the read system call isn't completed. It's reading on file descriptor 0, and it's just waiting. It's blocking. It's like, okay, I'm here until you give me some input. So we give it that input, and the read system call completes on file descriptor 0 with the character 2, which is 1 byte long. That's what that 1 at the end means. And after that's done, Python goes, great, okay, I'm going to wait some more. Because we haven't given it anything that to Python looks like a complete statement, so it's going to keep making read calls until it finds that complete statement. So if we do plus, we get that, and then if we skip to the end, once we hit a new line, Python's like, okay, I know how to process this whole thing as a statement. I'm going to go do some work now. If we were to write this algorithm for waiting for input until you find something to operate on in Python, it would look something like this. You have a loop. You read some characters while you're in that loop. and then you print the evaluation of the line once you're done with it. And I'm being very coy and trying to indicate that if you've heard of a REPL, the read eval print loop, this is probably the simplest algorithm possible for a read eval print loop. That's why those words are bolded. So, we have the Python process. It's got 3 file descriptors, standard in, standard out, and standard error. But if you think back, this is forked from bash, which theoretically has those same file descriptors. If it's got those same file descriptors, how does that mean my input gets sent to both? How does Python know it should be reading and writing as compared to bash? And it turns out that there's some special logic that sets Python as the foreground process, and bash says, okay, Python is the foreground process. I'm going to choose not to listen to any input or output until Python exits. This is also something that happens a little bit in the term.ios layer, which don't have a bunch of time to get into it, but there are some excellent blog posts that I can link to at the end. I don't have links right now. If you Google Nelhaj term.ios, he's got a series of blog posts that go into way more detail about how, rather than having paper terminals, we wrote some software to completely mimic the paper terminals with telephone line on modern OSs, and that's just crazy and interesting to me. Okay, so now let's talk. So now we're done. We've gotten our answer back. Python has seen 2 plus 2. It returned us 4. And we typed Control-C because we're done. Control-C is gets sent to term.ios, and term.ios goes, aha, I know how to interpret this. It's not normal input. It's special input, and this special input normally means signal interrupt, SIGINT, and that SIGINT gets sent to Python. Python, when it started up, bound handlers to certain signals, including to SIGINT. And so when Python receives Control-C, through term.ios, through the signal, into the Python process, it says, wait, I don't actually want to interpret this normally. It's a keyboard interrupt. It raises a keyboard interrupt when it receives that Control-C. So the Python process has at least 2 special cases for signals that are bound to the process. One is SIGINT, which we just talked about. The other one is SIGPipe, for moving data between processes. And so hopefully you know that Control-C doesn't end the Python process, it raises a keyboard interrupt. That's how that process works. Go back a little bit. Right. You hit Control-C, it goes through the term.ios layer like all the other characters. Python catches the signal, raises keyboard interrupt. Control-D also kind of has a special place in Unix. Control-D goes into, whoa, went too far. Control-D goes into the term.ios layer as well. And if this weren't Python, if this were another program like cat, Control-D would mean close the file descriptor. And cat would go, okay, I've got nothing else on standard in, so I'm done. I'm just going to execute and exit. For Python, it catches Control-D and says, aha, that means that the user is done with me and I can exit. There are 3 ways to exit Python, and they all kind of do the same thing. So one is Control-D, which is the equivalent of doing import sys and sys.exit, which is the equivalent of raising system exit. Hopefully all of these are a little familiar. And if we go back to stracing Python and skip a bunch of input, above there would be our read 0 to read 0 plus, etc. All 3 of those are going to result in an exit code of exit 0, no return. It's just done, and you get dumped back into the shell, which you can do because you're not running in the original process, you're running in the forked process. A cool trick that I didn't know until working on this, that some of you may know, some of you may not, if you do echo $, which is the variable that bash creates to say, give me the result of the last program running, the exit code of the last program running, and you do a 0, it gives you a 0. If you were to do import sys and sys.exit 1, and then do that same thing, you would get 1. So, full recap. I probably went too fast because I was worried about time, but I'm happy to go over things again and slow down and answer questions to the best of my ability. You start with the bash process. Bash looks for, finds, forks, and execs the Python process. The Python process has some file descriptors that correspond to a pseudo terminal, and it also binds some handlers to special signals on the operating system. I'm going to pause here. Probably should have some water. Oh well. And that's pretty much it. This is what it looks like at a high-level abstract view to your operating system when you ask it for the Python program, give the Python program some input, and then exit. That's the whole thing. And so as a conclusion, I'd like to say be curious about this kind of stuff. Like I said at the beginning, I'm not an expert. I and a friend did the digging to get this far, using these programs that we knew about and Googled and figured out to build this mental model in our heads to turn into the talk that hopefully you enjoyed today. And that's it. Questions?
Okay, so as I said at the beginning of the talk, if you had any questions, feel free to write them on a card and I'll collect them up now. Has anybody written any questions down? Okay, so then it's up to you. Would you like to field free wild questions?
Free wild questions. Yeah, I will field free wild questions. I make no promise that I will know the answer to those questions, but I'll nod and say, yeah, that's, well, my research indicates that, does anybody have any questions? Yeah, in the back. Why don't you say your name and then what's your question?
Sam, Lynn, S-trace, and what was the other?
Oh, yeah, let me go back a slide. So PS-tree, S-trace, and then file and hexdump.
So internally on the terminal, file and hexdump worked, but S-trace and PS-tree did not. Is there?
Are you on a Mac?
Yeah.
Okay. These commands are the Linux standards on Ubuntu. strace on a Mac is spelled dtrace, and it works slightly differently, but should still give you roughly the same stuff. PS3 is a weird one. I thought PS3 was still standard on a Mac. If that's not working, that's news to me. Did you try? You might. This would be weird. You might have to run it as root. Maybe the guy in the back knows.
You can install it with Homebrew.
You can install it with Homebrew.
Oh, it's not. It's not install. Yes. Okay. Thank you.
Yeah. Other questions? Yeah. Say your name and then give me a question.
Josh Burkess. To follow up on his question, dtrace is actually a lot more powerful than strace, but it's also a lot harder to use.
Yeah, that was our experience as well. But because strace doesn't exist on a Mac, it's kind of like it's what you got. Cricket.
Okay, well, if that's all, please.
Oh.
This is probably a little bit outside of the scope.
That's fine.
I'm wondering now exactly what happens when you create a virtual end to run Python.
Sure.
I was thinking those were simply links, but they're not. They're executables.
Yeah. So it's a little bit outside the scope, but I can talk about the best of my knowledge of a virtual env. When you type, in my case, because I'm using virtual env wrapper, mk virtual env, it's going to do some special setup of links. That's why when you do activate and deactivate, it's mucking with your path to point everything that Python needs at the local copies that it's made of like site packages and the local copy of the link to the actual Python executable. And it's making sure that the first place that your path looks is in the local virtual env that you've created, not in the system site packages. So you're right that it relates to that first step of bash looking for the path, but when you make a virtual env, what it doesn't tell you is that it's not like making a separate container, it's just changing your path to make sure that that bash is looking in the right place for the local Python, rather than the system Python.
But if I do a file on that copy of Python in my virtual end, it's telling me that it's an executable file. Is it making a hard link to that? Or is this a bit outside?
I don't know if it's making a full copy of the executable, but it might be a hard link. Does anybody know the answer to this one? I feel like the guy in the back might know the answer to this one. No? Okay. That was a good question, though. Yeah, in the back. Say your name and then give me a question.
Sure. Name's Thunder. So my question is, now that you have a deeper understanding of how Python actually is called, does that come into your coding effort?
It hasn't come into my coding directly. It's more, I would categorize this as more of a systems administration talk of like, hey, I need to do some weird things at the system level, or, what does it mean when, as an example, you might have seen in some tutorials or at the end of the command, you do a bash command and then 2:&1. What that's saying is your 2 is a file descriptor, 1 is a file descriptor. You're redirecting 2 into 1, so you're redirecting standard air into standard out, so that they're both going to the same place. And so it's that kind of stuff. It's understanding what's going on under the hood at a system process level, so that if, at the end of the day, programming is making your system do what you want it to do, and so is system administration. It's helping me gain a better understanding of my system isn't doing what I think it should be doing. How do I fix that, and how do I make it better? Having an understanding of how processes work can help your programming if you're writing a lot of things that make use of, is it Schlex? There are Python libraries that I'm forgetting the name of right now that will do a lot of this. That will, you can do os.fork, for example, right? And you can do os.exec, and you can, you have access to these commands from within Python if you were writing something that required, making multiple processes rather than making threads. And because it came up in the last talk that so this talk has been given before, it came up last time, and I'll make a note. There is a PTY and a TTY library in Python. What's the difference? TTY is setting, as best my understanding after looking at the standard library docs, TTY is setting line options for how the actual terminal reads characters, and PTY is doing more formatting and things that you might use to set up end curses, or basically making the terminal prettier. Whereas, think of TTY library as you're actually mucking with the actual terminal connection. PTY is mucking with the display at the terminal. Free question. There you go. Are there any others? Whoa. Am I way? Yeah, go ahead.
One last one. So you talked about the bash shell copies, bash Python, so it doesn't do process completed.
Right.
And this, how do you? Because I was trying to follow you here, and then I got process completed. And I was done with the shell. How do you avoid that? I missed.
Yeah. So.
How do you make sure that happens?
Yeah. Here let's go back. Oh yeah, I can repeat the question. So the question was, if you actually try doing something say, went too far back. If you do exec Python in your shell, now I gotta go forward. So if you do something like exec Python in your shell, and then you quit Python for whatever reason, you would get that process completed. And the way that bash avoids doing that is by forking itself, so there's a separate process. And now Python is running in this separate process, and nothing, to the best of my knowledge, that you can do to this separate process, PID 1222, nothing you do to that process can kill the bash shell. I'm sure there's some exploit or a fork bomb or something that actually could kill the bash shell, but nothing that you would do in a normal operation would kill the bash shell. So now when Python exits, you're just going to get dumped back to bash. You're not going to get a process completed. Did that answer your question?
Yeah, but that didn't happen. I was following you along. How do you make sure that happens? That it's making that copy.
I don't know that you can call fork at the terminal and have it work the way you're expecting.
Okay.
Yeah, I don't know, actually. That would be really interesting if you could step through all of the pieces where you call fork and then step into the fork and then run exec. Because I think if you run fork, it's going to create a new process, but you're still going to be in bash. So then when you run, let's say you're in bash and you're able to call fork. It's going to create a copy, but it's not going to put you in that copy, right? You're still going to be in the original. So if you call Python on the original, exec Python on the original, and then kill it, you're going to get process completed. And now you're going to have this ghost bash just kind of running over here going, hey, I'm doing it great.